Welcome to the chapter on tribology, surface roughness, and in machining processes. So, let me brief you about what I am going to discuss in this chapter. So, chip tool tribology, tool workpiece tribology, that means cutting tool workpiece interaction, which is not that much important, but however, I discuss slightly, and sticking and sliding zones in the chip tool surface and types of lubrication. Then I will go to another area of this chapter, that is called surface roughness. So material removal rate in turning process, how do you calculate material removal rate and all those things. Then followed by the machinability. Machinability is nothing but the ease of machining, how and all those things. So currently what I am going to deal in this class is chip tool tribology. So majorly the class revolve around chip tool tribology. How do you measure the experimentally by using the tribometers and all those things. Tool workpiece tribology is not discussed much, but however I will just brief you. Sticking and sliding zones, which are nothing but the part of chip tool tribology, types of lubrication. Okay. So coming to this one, chip tool tribology basically came into existence, or first they started in 1970s, where interactions are studied. Okay, so you can see that's one, and during that what they have done is they have taken the transparent sapphire tool. Normally the sapphire is one of the hardest materials, so they have taken it as a tool. Okay, since the hardness is most important in cutting tools, so they have taken it. Normally nowadays, if you see, the sapphire is commonly used as a nozzles for abrasive jet machining or some of the advanced machining processes, the abrasive processes. Okay, so they studied using this one, because if it is transparent, so they can understand how the chip flow and how the stick slip phenomena takes place and all those things. Okay, so if you look at this picture, we have two zones. One is a sticking zone, another one is a sliding zone. Okay, so this comes under the zone 1, that is called sticking zone, and comes the sliding zone. Okay, there are the two zones. Okay, so these zones, in the sticking zone, chip material stick to the rake surface of the tool, so normally it will have a perfect contact. I'm not saying that perfect means 100%, but it is having a good contact. In the sliding zone, it slides across the rake surface. This is the two surfaces. One is the sticking zone and the other one is the sliding zone. Okay, so if you can see how the sticking zone and sliding zones are differentiated from this point of view. So this is experimental, which we have recently done some of the work in this area for understanding the basics of the chip tool tribology. So if you can see the cutting tool machining the workpiece, in this case carbide tool is machining the stainless steel. So for understanding, if you see the primary shearing zone, if you, this is the experimental one, experimental picture. So this is a schematic one. How we are analyzing is schematic one. If you see this one, what will happen, this is primary shearing zone and followed by the secondary shearing zone, which is most important in this case. Primary shearing zone is because of the severe plastic deformation. In the secondary, normally we deal with. If you see this area zooming, we have a sticking region and followed by the here it represents the height of deposition that is taking place. So the red color and white color that you are seeing at this position, this stands for the peaks or the height that is forming. Assume that this is my surface, how the things are piling up on top of it. So built up edge formation and all these things are studied there. Okay, so that's why this is green region, height is slightly less. So that's what the beneath the chip material is adhered to the tool material. If you see the sticking zone surface roughness and sliding zone surface roughness, how it will changes and all those things. If you see in the previous slide, you have seen the sticking and sliding regions. If you take the surface roughness of the sticking zone, normally you will have a very rough surface. Okay, so you can see the 3D profile, 3D roughness profile. Normally this will taken from the non-contact surface profilometer. So this is a 3D surface roughness profile. So you can see the completely, it looks like a some craters are formed and some deposition is taken place. This is completely random. This is corresponding to my sticking region. In the sliding region, basically there won't be proper contact. Okay, in the proper if there is no proper contact, what will happen? It will slide, the chip will slide on my workpiece. What is happening here is, if I have a workpiece and my tool is there, chip will move like this. Okay, so the first portion is this sticking zone, the next one is a sliding zone. So there is a gap, it forms like a wedge type of thing. What will happen? This is the sticking region, and in between you will have a sliding region where you will have asperities will rub against and it will form its own lines. Okay, that's why this is called sliding region. So these are forms the sliding marks. You can see the sliding marks. So what you are seeing, these lines are some of the textures that we have done, but it is nothing to do with the current physics what we are talking about. These are the sliding marks. Okay, that's about the thing. See, now we will see the surface morphology, how the surface morphology, because the surface morphology plays a major role. Okay, the surface morphology means how the surface look like on the surface. That is called as a surface morphology. Surface morphology includes surface roughness. Okay, so coming to the sticking region, if you see the surface, it is completely rough. If I am taking this one is a 3D surface profile, surface roughness profile, and this is 2D surface profile. So this is 2D surface profile. If you see the sticking region, if I am measuring in this region, normally some of the average region, if I take any randomly some of the regions that I take, normally this will have a peaks and valleys. This is a peak and these are valleys. Okay, so this is a sticking region. So this is too rough. At the same time, if you see the sliding region, the beauty about the sliding region is will have a gradual flattening. Okay, if you see here any surface in the sliding region, normally these are the sliding region. So you have a rough surface here, rough surface, and it is smoothly going. Okay, that is what you can interpret here. You can see the surface, it is a rough zone here, but this roughness is much lesser than the sticking region. Then normally it will become partially flat region. Okay, it's called flat region. Okay, so that means that there are marks on the surface, and where marks, then it will become flat. Okay, so that is the beauty about the sticking region and sliding region. The surface roughness in sticking region is much higher compared to the sliding region. And also you can see that if the sliding region, to the start of the sliding region to the end of the sliding region, you will have a very rough to the flattening surface, and then onwards you can see the completely flat surface because there is no interaction between tool and chip. Okay, that's about the surface roughness in the tooth chip interface. Okay, so normally if you see a commonly question, so why the forces are high in when machined with the wear tool? Okay, so if I ask you a simple question, like I have a zero rectangle tool, this is a zero rectangle tool, so I am having a positive rectangle tool. Rectangle is alpha equal to 0, alpha is positive. Okay, normally here force equal to F1, here force equal to F2. If I am giving a zero rectangle tool, okay, with crater wear basically. So crater wear looks like in terms of depth, crater depth we measure it. So we measure in terms of this one. Okay, in that circumstances, what will happen? It looks like a positive rectangle. Okay, here force is F3 In generally what we study about the forces, normally F2 less than F1 and F3. But if you see the geometry wise, if I just remove this portion, weird portion, what will happen? So you should get F3 also like F2. Normally the if the rectangle is 0, my forces are F1. If my positive rectangle, forces are F2. Normally positive rectangle experiences less forces because chip flow will be uniform and there is no, it's aerodynamic and all those things. In terms of zero rectangle, the frictional forces is very high because the chip will move parallel to the rake surface. Okay, that's why normally F1 is higher than F2. Okay, if the tool wear takes place, that is crater wear takes place, in that circumstances, the force basically experimentally it will increase. But geometrically, if you see, it is resembling like your positive rectangle. These two are looking alike. In that circumstances, F3 should be less than F2, but this statement is wrong. Why? So, to answer this one, we will see the things how to handle it. If you see the surface roughness in sticking zone, normally whatever the surface roughness that you are putting in the tool, what will happen? This is completely rough. At the same time, if you see the tool wear is starting slightly ahead of cutting edge. It is not from the cutting edge. Normally whatever the angle that will give is starting of this one, so that it will be having a smooth flow. But here the roughness is very high. At the same time, it will start away from cutting edge. These are the two reasons. There are many other reasons. Okay, so these are the two reasons that why normally F3 is much higher than your F2 and F1. Okay, because tool wear may be geometrically same, but it is not so practically the forces are very high because of these reasons. As the sliding region also, it will have the negative effect because of the sticking and sliding zones surface roughness. So obstruction will be there. If the obstruction is there, the frictional forces will goes up. Normally there are two mechanisms. Whenever I already told you when I am talking about the tool wear mechanisms. So there are two types of abrasion takes place in the chip tool interface. One is a two body abrasion. So two body abrasion means when the two mating surfaces are abraded each other, okay, because of the relative motion. Okay, one is moving in this direction, another one is moving in this direction. Because of relative motion between two bodies, if there is a wear and tear takes place, that is called two body abrasion. So if the mechanism is abrasion, so the three body abrasion means whenever two bodies are abrading each other, are moving relative to each other, and if there is a third body which can rotate about its own axis is in between them. Normally what I mean to say is that if the chip tool interface is only interacting, that is called two body abrasion. Some people nowadays are using the nanofluids as a cutting fluids. So nanofluids will have particles. At the same time, there is a possibility of the tool which is made up of powder metallurgical. If the binder is loosens and goes off, what will happen? It may releases the particles into the chip tool interface region. This also has one probability that the particles come into the chip tool interface. Because of this, you will have these particles are no more adhered to the tool material. Okay, so they can rotate about their own axis because they are independent enough. In that circumstances, it is called a three body wear. Why I am talking about two body wear and three body wear is nothing, is how we have to measure two body abrasion and three body abrasion approximately using experimentally, because tribology is itself is a big subject. Okay, we have to correlate with respect to machining. So there are some standards, ASTM standards that one can follow. Okay, so however, the abrasive wear resistance normally is a function of hardness. If the tool is much harder, what will happen? So what will happen? Normally the wear resistance will be more. Okay, hardness is nothing but resistance to penetration. If the penetration is less, what will happen? Abrasion is less. Okay, now you understood what is the difference between two body abrasion and three body abrasion. Okay, So three body abrasion takes place when there is a chance whenever you use the nanofluids as a cutting fluids or solid lubrication if you are using, or whenever you are using whenever your tool got when the temperature of the tool goes high and binder goes loosened, then the particles of the powder metallurgy tool, some of the particles may come and in between chip and tool may have their independency. In that circumstance of three body abrasion. Okay. So this is about the two body abrasion as well as three body abrasion. Okay. So because of this two body abrasion as well as three body abrasion, there will be a lot of frictional heating takes place. Okay. So the frictional heating, normally the frictional heating will takes place in terms of in the region where chip tool interface region. Okay. This is the region. So the rate of energy input in the friction is the product of frictional force and the sliding velocity. Okay. So this is the multiplication, or the, if you multiply frictional force and sliding velocity, normally you will get the frictional energy. Okay. So the normally perhaps 5% is consumed or stored in the material. This frictional energy, what will happen if it is stored in the material? What the temperature goes up. If the temperature goes up, what will happen? Microstructural defects. That means that if you have seen in your earlier courses, if you see what will happen, there is a cold rolling, hot rolling in the metal forming processes. If the temperature goes up, what will happen? My microstructure will change. For example, if you see blacksmithy, if at all you want to make or sharpen the knife, what will happen? You just put into the fire, then after 10 minutes or 15 minutes, just you will take out the orange red one. So then, because the number of atoms in the knife is same, but the thing is that whenever you take skin out after some time, what will happen? It might have slightly bulged enough. Why? Because the microstructural changes taking place because of the temperature. Then what you will do, you will take on the edge and you will hit it so that it will become sharp. Then you will put into the water so that again it will go to its original microstructure. May not be 100% original microstructure, it will go. So the sharpness will increase. Okay. What the bottom line of change, it is microstructural. So because why the microstructure is taking, microstructural change is taking place because of the temperature. If the temperature is stored, what will happen? The microstructural defects or microstructural changes will takes place. Okay, that's about. If the temperature is still more, what will happen? There will be defects, cracks, and all those things will takes place. Okay, so this is about the frictional heating drawbacks. Okay, so frictional heating is dissipated as a heat. Normally, whatever, if the frictional energy, whatever these stored energy, it can dissipate as a heat under certain conditions, and melting of the sliding interfaces also can take place. Okay, so if the temperature is up, these are the sliding interfaces. This is the sliding interface. Let me show you. This is the sliding interface. Okay, okay. What will happen? This may melt. Okay, so normally that mostly the workpiece is much lower hardness than the tool. At the same time, if the temperature is high, normally the temperature that is carried away by the chip is always higher, that is 80 to 85%. So beneath the chip always there is a melting tendency. Okay, not in all workpiece materials. Those workpiece materials which are soft enough, whose melting point is low, these type of things will have a melting tendency. Okay, so this is about the frictional heating. So what are the basic problems with the chip tool tribology? Okay, why we have to study? We have already studied this, what I am going to show you, but it is a interlinking. Okay, everything you have to interlink whenever you study in the past in this course. So some of the metal cutting course and metal fluids having, it is a single subject. So always some things analysis you have to take from there and you have to correlate and all those things. Okay, so why you want to study is if the tribological conditions are bad, that means that if the tribology is very high, then your input energy will be very high. That's already I have shown you in the previous class when I am telling about the forces in the machining operation and all those things. We have seen the tan beta, that is called coefficient of friction is nothing but F by N. So if your N is high, what will happen? Frictional force is very high, then your waste energy will be very high. If you see the complete, the normally work done or energy input, if you see what will happen, Fc into V, or energy input, shearing force versus multiplied by shearing velocity. This is called useful energy. Frictional force multiplied by chip velocity, this is called that will go as a waste, that we have already seen. So if my frictional force or the tribological conditions are bad, frictional force will increase. If my frictional force increases, what will happen? This particular part of my energy will goes up. If it goes up, what will happen? My input also will goes up. Okay. So for that purpose, you should be always careful and you should study the rheological things. Okay. So that's why we have to measure coefficient of friction and all those things. So now coefficient of friction you have already seen. Just I have just want to give you glimpse F by N. In the previous class, if you see how you calculate F is F sin alpha plus Ft cos alpha is 1, and N is Fc cos alpha minus Ft sin alpha. So if you place both, what will happen? You will get a final equation that is called mu equal to coefficient of friction, that is Fc sin alpha plus Ft cos alpha by Fc cos alpha minus Ft sin alpha. This is what you are going to get. Okay. So determination of friction coefficient you have seen, and the basic assumptions normally what we consider in this one is normally F and N, which are there on the tool rake surface. This is the rake surface, this is the region. Okay. So now these are all uniformly placed. Okay. But however, this is assumption is not so realistic. Okay. So that's why what I want to say is that applied forces, that is F and N, are uniformly distributed over the chip tool interface. That is the assumptions normally whenever we want to derive some equations like Merchant equation or Lee-Schaffers, some of the equations whenever we want to measure we want to calculate the shearing angle and all those things. For that purposes, normally we take F frictional force and normal to the frictional force, coefficient of friction and all those things. Okay. So we assume that these are all uniformly distributed on the rake surface. However, this assumption is not so. Okay. So we will see why it is not so, though in terms of stresses distribution on the metal cutting we will see, because the sticking zone region stresses are different. I mean to say F and N, and the sliding zone F and N are different. Okay. So this is the chip tool interface, this is the cutting tool, and the chip is coming here. Okay. So nowadays the contact pressure will be maximum at the tip point and gradually it will decrease. This is stresses. Okay. However, we have seen in the previous slide the assumption that it is uniform, but it is not uniform. You can see it is at the tip, it is maximum and it will become a minimum as it moves from the tip. Okay. That is what we are seeing here. You can see the primary shear zone, which we have already seen, rubbing action, that is between the workpiece and the flank face of the thing, that is called tertiary normally shearing, and secondary shearing, which we are talking about and we are talking in this one also. So rubbing zone, basically this will takes place between workpiece as well as the flank surface. So this is not that much important. However, I said in the starting of this class that we just give you the glimpse. That's nothing but if my frictional rubbing between the workpiece is very high, what will happen? The surface roughness that you are generating and the final product will destroy. I mean to say the surface roughness will increase. If it is increases, what will happen? It may not qualify the quality check. Okay. So for that purpose, always you try to avoid by putting the cutting fluid or any tool coatings or something. Okay, so since normally if you have given a relief angle or a flank angle properly, so that can itself is a good thing for from the rubbing action against the workpiece. I mean to workpiece means I mean to say the final product that is coming out. Okay, if you can provide the lubricant jet across the workpiece and tool interface, that will also fine. So in order to this will help the workpiece and tool flank surface interface. Okay, but not much study has been done in this area, but some of the researchers they have done in this area by putting a multi jets, one jet on the tool rake surface where the cooling property of the cutting fluid is much better. Another one they are putting on the workpiece, that is a final product, and tool flank surface they will put where lubricating nature of cutting fluid is good. This type of things they will do. Okay, so people, if somebody is interested to take the research in this area, so there are some of the papers who talks about the multi-jet based turning processes where they will use as I said one jet which is having a better cooling properties. Better cooling properties means water based coolants on the chip tool interface, and less water content or the mineral oil content cutting fluids on the flank surface. You can try, and in the advanced materials, some people who are PhD student who are seeing or who are watching my slides can take up multi jets. Assume that if I want to machine the titanium with CBN or coated carbides, so you can use similar technologies. Even you can use some other technologies like cryogenic on one side and another side mineral oil based and all those things. But you should be very careful because how to recycle it, because once it go back to the cutting fluid tank, then how to recycle it and all those things. And you should be taken care about the lathe bed or machine tool bed and all those things, because cryogenics also involved here for the better cooling ability and all those things. Okay, if you see the normal forces and the coefficient of friction is okay. So okay, the actual distribution of shear and normal stresses on the rake surface of the tool is probably from the shown figure. So if you can see the normal stress, this is normal stress and this is the shear stress. Okay, so this is sticking region. And this is a sliding region. Okay, so the stresses you can see here, this is the normal stress and this is the shear stress. Okay, the shear stress is constant in the sticking region, but however in the sliding region it is gradually decreasing. Okay, as you can see here, this is a constant in the sticking region and it is decreasing gradually to the minimum from the maximum of sticking region to minimum in the sliding region. However, if you see the normal stress, that is N normal to the this one, so it is gradually, it is maximum at the tool tip surface, this is called tool tip, to maximum here, and it will gradually decrease to the minimum at the end of the sliding region, beyond which there is no tool chip interface is not there. Okay, if you see some point C, the normal stress is very high and the metals adhere to the tool rakes, resulting in the sticking friction conditions. This is the normal stress. Normally if the normal stress is very high, that means that normal force is very high for the same area. So what will happen? This causes the sticking in the region, because of which there is a built up edge formation will takes place and all those things. From C to D, where the chip curls, smaller normal stresses are obtained and giving the result sliding friction conditions. Okay, C to D, which we are studying in, this is a sliding region. because of the normal stresses are low here, what will happen? There is a sliding action takes place, and since there is not much stresses on the tool by the chip, and if you have a cutting fluid application also in this one, if there is a cutting fluid, not much difference, but there is a difference. What will happen? There is just a slight rubbing action will takes place. Wherever the stresses are very high, there sticking will takes place. Where the normal stresses are low, there the sliding action will takes place. That is what this normal stress and shear stress distribution want to tell. Okay. If you take the analysis in the contact surfaces, basically AR is the real area of contact and A is the apparent area of contact. If you see the normal force versus frictional force, that is called F versus N. Okay. So, if your normal force in this region 1, what will happen? Your AR by A is approximately 0. Okay. Now, see what is meant by real surface area of contact and what is apparent area of contact. If you see here, this is area is complete apparent area of contact and real area of contact AR. Okay. Real area of contact in chip tool interface, I am talking about metal cutting, that is why correlating to the chip tool interface. So, AR only it is at certain points, basically if this is the point and this is the point and this is the point. If your area of contact is approximately, apparent area of contact is in mm normally, because it is a complete area that we are talking about, but real contact is some points. That means that it may be some few nanometers or micrometers. If you take the ratio of real area of contact to the apparent area of contact, where nanometer by millimeter is a big area, where it is some about, assume that it is more than 1000, 10,000 times. That is why it is apparently 0 in this area. Okay. Slope is nothing but your coefficient of friction. But if you see in the another region, where this is the region, if you see, if my area of real area of contact is equivalent to area of apparent area, then it is relation is 1, contact between. Okay. In this region normally it is 1. Okay. Because the contact area is same. For that purpose, normally load conditions will be high and the velocity will be very low. In this condition, velocity will be very high and load will be normally low. Okay. This is about the two forces and real area and this contact area and all those things. Okay. So, now how to study this tribological aspects, tribology of metal cutting in experimentally. Can we do some machining test or how to do? Okay. So, for that purpose there is one standard is ASTM G99 one standard. One of there are many standards, just I am telling you about one standard method for wear testing within a pin on disc apparatus. This pin on disc apparatus is one of the tribometer. Okay. So, this is if at all I want to test it, what will happen? This is a simple pin on disc. Okay. I mean to say there is a pin is there, on disc is there. This is the disc. Okay. You can see this is the disc. And this is a pin. Okay. This is the holding position is there, but however you can see a pin here. This is the pin. Okay. This pin will be touching the surface like this. This will be hold. Okay. If at all I want to machine a mild steel with respect to HSS, how I have to do? Okay. So, now what will happen? I will make a steel disc and I will make a pin HSS. You can make HSS pin by using EDM process. Basically you take a HSS block, then you use the iridium process and you can cut. Normally the size of the pin, that cylindrical pin that one can use in the, as per the standard is 6 mm diameter by 15, above 15 mm you can use. Normally what people take in the range of above 15 mm, 6 to 8 mm normally they will, people will take. Okay, so this pin you will hold here, you are holding a pin here and you are giving some input conditions. What are the input conditions that you are going to give is normal load. If you see here, there is a load cell is there and you have to put, this is the one that is a cantilever beam type it is holding. So you can put a load connecting to it here, load on other side which is not visible here. So you can put load. So that is how much load you have to put. Sliding speed. Sliding speed is nothing but how fast you are rotating your disc. Okay, so whether you are rotating at 60 meters per minute or 30 meters per minute. Wear track diameter. So whether you are giving this track or whether you are giving this track. Sliding time. So how much time? Normally whenever you want to do 1 hour, 2 hour, 24 hours or 6 months. Some of the experiments we run for 1 week also continuously to understand these things. Okay. Some of the conditions also we will explain. As I said, ASME is G99 we are normally will be used for the pin on disc wear testing. So the conditions, for example, what we have used is 19.6 newtons is the normal load and 30 meters per minute is the sliding speed, wear track diameter is 50 mm and the sliding time is 1800 seconds, that and we can measure. Okay, here if you see there is a slight difference between the previous slide where you would see here the disc and pin are there. Okay, this is holds good for 2D abrasion. Okay, why? Because you are having a HSS which is a solid material, at the same time you have a workpiece material mild steel, so you are testing it. Okay, there is a very less chance that the particles formation between these two mating surfaces. That's why this is 2D abrasion. However, you can also simulate or you can also do the 3D abrasion by placing a emery paper, that is called abrasive paper, on the disc. So you have to hold it firmly. You can see the abrasive sheet here or abrasive paper. So and you just move around. This is 3D abrasion. Okay, so you can also check 2D abrasion as well as 3D abrasion. 3D abrasion, some of the people will follow for grinding applications and all those things. Okay, so if you see the setup, how to measure, this is the pin on disc, this is the POD pin on disc setup, this is called data acquisition. You can see this is the data acquisition system. Okay, so now data acquisition will give to the CPU and computer. However, we can also measure the infrared camera, what is the temperature generation and all those things. This is the infrared camera is also attached. This will display will give me forces. I can calculate coefficient of friction and all those things. Okay, so my infrared camera gives me the temperature, how the what is the temperature generation takes place for the normal condition. If I am using the lubricant, how the temperature varies and all those things. Okay, so if you see the same picture in a good way without what and all those things. So this is what the abrasive paper is, and this will give you the, now I will show you how the abrasive sheet and my workpiece or the tool material If I want to understand the workpiece material nature, I can use a pin as a workpiece material. If I want to use the tool material versus abrasive sheet, I can use it also. Normally, the pin will be basically made up of tool material, because we will understand with respect to tool materials only. Okay. In the Zoom version, if you see 3D body abrasion, this is the track. You can even see it is running. Basically, this is the track. Okay, so track is there. So this about the 3D abrasion, and you are capturing the temperature profiles also. Okay, you can see how the temperature is shown here. So the same track here, whatever the experiment that I am doing at this practically, I am also catching the image in the infrared camera, where I am also observing the temperature. Okay, so normally the temperature is about 60 to 70 to 80 degrees temperature it is recording. Okay, so since the experimental conditions are too low for demonstration purpose, for what is the temperature effect and all those things, to show you, we have done a simple sample experiments as a part of our research experiments also. Okay, so you can see the temperature of the track, you can see the temperature of the pin and all those. Okay, so this is the temperature of the pin, and this is the temperature of the track temperature. Okay, your pin is situated here. Okay. This is about the 3-body abrasion as well as the temperature measurement and all those things. Okay, because we were talking about the frictional heating and all those things. This is completely because of the frictional heating. The temperature is raising around 70 to 80 degrees. So it is a huge amount of temperature. Okay, not in the machining operation, the severe plastic deformation is giving you major temperature. Apart from it, frictional also is there. So if severe plastic deformation is giving you the major amount, and frictional heating also gives you some part. Okay, because of this, the temperature goes up. Okay, another one, normally to test the tribological aspects, the scratch tester also used, because whenever there is a tool coatings are there, in that circumstances, what is the load, what is the speed at which this delamination of the coating takes place. For that purpose, for that type of tribological aspects, normally scratch test based tribological conditions are used. This is the diamond indenter normally, and you will give a reciprocation. Assume that I have a tool in this form, so I am just using the reciprocation. So how the reciprocation? You can increase the lamp, I can give this. So I can, with different loads and scanning speed, if you do, what will happen? The scanning, the shearing of the tool surfaces will goes off. It can be tested for the virgin tools, or it can be tested for the coated tools also. So in that circumstances, you can see where the delamination in terms of tool coatings, you can see at what load and what speed the delamination of the tool coatings is taking place, that you can study. Okay, so in this way, what one can study is the pin on disc. Experimentally, you can study the 2-body abrasion, 3-body abrasion. If at all I want to study the delamination of the coatings, you can go do the scratch testing. This scratch testing is also one of the ways of doing the tribological test. Okay, this is about the tribology as well as this one. Still now we have studied the what is the chip tool tribology, as well as how the frictional heating takes place, on how the tool wear is can be simulated in terms of tribology. I'm not saying the tool wear. So normally tribological conditions can be done experimentally, and if at all normal tools you can do by the pin on disc, where workpiece can be the disc as well as pin can be the tool material. And if I have a coated tools, nowadays people are talking about advanced tools like nano coatings or micro coatings are taking place. For this purpose, normally you can go for the scratch tester also. Okay, this is about today's class.